Hello, and welcome to this webinar, looking at getting a better return for your emulation investment. My name is Stuart Taylor, and I'm a product manager at Altair Engineering. I'll be describing what is essentially a new product called Hero. It allows teams to share precious emulator resources efficiently. A hot topic for emulation is the efficiency or usability of the emulator resources. This is typically the ratio of the number of gates in the design as compared to the number of gates consumed by the design on the emulator. Efficiencies of 65 to 80% are typical. But this is a one-dimensional way of looking at efficiency. Effective utilization over some period of time, or the number of simulation cycles per week, is another. And when we look at those metrics, we find that the 80% efficiency number is much lower. If we're restricted to using the emulator to just regular work hours, then the number drops to less than 20%. Often regular work hours might be restricted to just interactive or ICE jobs, in-circuit emulator jobs, those that require or expect a human to be present. But suppose we can run batch simulated acceleration jobs overnight. Won't that dramatically overall improve efficiency? Well, it certainly helps, but it does present many challenges. The emulator needs to be shared across multiple teams. So how do we do that? Hard partitioning of the emulator to allow some balance across teams leads to its own inefficiencies. The SA runs often get stuck. It is, after all, development. And so the overnight regression doesn't complete overnight, and instead running during the day, which clashes with the next round of ICE jobs. Further, the SA jobs are often waiting on a compilation to complete. How can we keep simulating while we wait for the new design and then cut over automatically to the new one when it becomes available? Eventually, we're faced with some technical challenges that are unique to the emulator space, but also challenges that are familiar to those used to sharing compute resources across multiple teams with multiple objectives. And that's where Hero comes in. All the features provided by a sophisticated batch queuing system, plus some of the extras to deal with the unique problems in the emulator space. So what might be better metrics than just gates per emulator? Well, we see two areas for optimization, simulation cycles and interactive debug job turnaround. The text in green shows the areas we think Hero can help. So looking at simulation cycles per week, that's certainly a metric that makes sense in the design verification space. We could also look at the number of tests run, assuming that we have many discrete tests, often the case in simulated acceleration, where we're attempting to co-develop both hardware and software. But plain simulation cycles per week, or number of test runs, hides another important factor, and that's the lag between the design release being available and getting a compiled version of that design onto the emulator. Compilation may take several days, and if it becomes available late on a Thursday night, we might want to load it automatically and start tests right away. Indeed, that's one of the goals of Hero. And we're calling it the compile simulation pipeline. Once we're promptly simulating a fresh design, we need to think about making sure that it's efficient. We'll cover how to run multiple jobs against a single loaded design and how to make those test sets robust against runaway. Turning to interactive or ICE jobs, one of the challenges of focusing on SA is that it's difficult to get an interactive job started quickly. So our second metric is time waiting to get an interactive job started. Some of the techniques that we have for this are preemption. And there's also an idea of a reservation for named resources at some point in the future. Two other factors are important too. First, we need good visibility and metrics, and we can only optimize what we can measure. Hero, with its background in regular batch queuing, has a rich feature set to do that. Then we must ensure that sharing across the design teams is easy to manage and understood by the stakeholders in those essentially competing teams. In the following slides, we'll take a look at how those techniques are implemented by Hero. First, a brief history. One of the unique challenges of emulation scheduling is the packing problem. Now, this is often called the Tetris packing problem by emulation users. We can think of each emulation job as having a certain shape, and the emulator, assuming it is already partially populated with jobs, a certain set of holes which the job can be placed. In practice, this is a hard problem to solve, and scheduling complexity is several orders of magnitude harder than placing a regular compute job on an ordinary Linux host with amorphous RAM and CPU resources. Our customers try to solve the problem with the regular job scheduler. While successful, the capacity was very limited. And we came out with the first emulator scheduling product aimed at the Palladium Z1 for SA workloads in around 2018. In this narrow use case, we were able to get utilization numbers of over 95% on a weekly period. We now have a complete rewrite of that product, one that is aimed at the broader emulation space, including mixing ICE interactive style workloads with simulated acceleration and supporting a mix of different emulators. It's worth a moment to see how the various compute resources can be classified. At the top, we have regular CPU jobs. Compiling the design may take a few minutes, and scheduling such a job is moderately hard. We have to consider CPU and RAM and software licenses, and as well as the usual stack of policy parameters. For that, we get a simulation frequency of about 1 Hertz. Now, we can run a lot of jobs in parallel, perhaps 20 or 50,000, so our effective simulation is in the 20 to 50 kilohertz. Costs using a data center style hardware is modest, those software licenses begin to add up. Now let's look at the big emulation players, Palladium, Zebu, and Veloce. The frequency of those are dramatically higher than even the parallel version of our CPU simulation, but so is the cost. A single emulator may run several $1 million, and that doesn't include the dedicated team to support the special workflows it requires. Now, since that we've spent so much, it's worth asking how hard is it to pack jobs on it effectively? And the answer is, partly related to the Tetris problem, is hard. But if we can solve this problem, we're now making much more effective use of these expensive resources. So a hard problem, but one with a big return. Now, Hero will also work with prototyping products like Synopsys HAPS. There's not much of a win there because scheduling HAPS, assuming it's a single predetermined design, is actually trivial. But Hero will make it easy to manage a mixed bag of emulated resources. So Zebu and HAPS, for example, can be managed from a single Hero instance. I've also added GPU here. Obviously, that's not an emulator, but with some of the new families of GPU, we can slice and run multiple jobs. So it's a similar problem to Tetris packing, and Hero can do that, but it's not our focus for today. So some key features of Hero. First thing is that it's an emulator-agnostic queuing solution. We have an abstracted model for various emulator types, and the supported emulators today include Palladium Z1 with a Z2 in progress, Zebu Z4, and HAPS. And we're looking for field experience on Protium, Veloce, and Zebu Z3, although we expect that to be very similar to the Z4. It's easy to set up and install. It's built on the well-established Accelerator code base, and it's got support for ICE and SA use cases. It leverages our core scheduling code, which is C++ and highly performant, but we've put in some optimizations for the specific emulation cases. Rich scheduling parameters like job classes, reservations, limits, and fair shares are all supported, as is a solid reporting and resource utilization set of dashboards and metrics. It's got a simple abstracted web UI, and it can also run some of the support jobs, the compile, test gen, and scripts on the attached emulator host as well. So it's easy to set up and install. The first thing you do is you install a software product, unpack the tarballs, and then we can create a queue with the HEMGR start command. In this case, we've named it Hero. Then we can edit the master configuration file to tell it about the various emulators and their types and where they can be found. That's typically host names and IP addresses. We compile the configuration file, and then we can quickly check the status, saying above Tasker Manager show, and then run a test job. Here it's a 5-module Z4 job. This is a picture of what it looks like in practice. I have a single Hero queue fronting multiple emulators, potentially of different types. I run a job expressing the resource requirement in terms of a span. And in ZBoo, this equates to modules. In Palladium, the mapping is boards. So on the top, we have a resource going to a ZBoo Z4. We tell it with a resource string -r hero, and on below we have the Z1. So monitoring, you can only optimize what you can monitor and measure. So let's take a look at some of those real-time measurements. Here we've got the hero runtime status. We've got the top panel shows the Palladium Z1. All of those 38 slots are empty, they're green, and that's telling you that there are no jobs running it. In contrast, in our Z4 group below, we've got 3 emulators. The first one, cluster 0, is running 2 span 5 jobs and consuming 2 runtime hosts and a total of 10 boards. Cluster 1 below it is running 3 jobs and consuming all of the runtime hosts. Those are represented by the capital H's. And in cluster 2, we've got, again, 3 jobs running, but we've also done some deconfiguration. We've deconfigured the first set of modules, and those are shown by the purple boxes. Job view, we've got queue jobs. This is showing us various different weight reasons for those jobs. It's a little tricky to read because of the complex emulation resources, but we can see that we've got a total of 48 jobs queued. We've also got some running jobs listed below. So taking a look at the runtime statistics, we've got some panels showing where bottlenecks might occur. We've broken it down on a per emulated basis. And we've also, on a separate page, actually a snapshot shown below, got the total number of jobs queued and running jobs, and also the jobs and turnover. The next panel is calendar-style time-based reservations. This is showing 3 reservations, 2 of which are currently active. Those are shown in orange, and 1 is going to be active in the future. This is going to be useful for scheduling ICE jobs against. We're essentially able to reserve things in the future, and this gives you the foundation for booking resources, almost like conference rooms. Hero itself has got the ability to track leaf modules and boards, as well as the job count. Key parameters about each job are also recorded and logged to both CSV files and Postgres. Additionally, there's an interface to monitor where we can treat the module usage just like license checkouts and use the same rich reporting techniques such as heat maps and efficiency charts. Okay, so turning to a specific use case, it's going to be ICE and interactive modes. This is really like scheduling a human and emulation resources together. So we think of this as a bit like booking a conference room for a meeting. The basic strategy is to create a reservation for a known set of emulator resources, specific boards or modules on a specific emulator for an agreed time in the future. The reservation cannot conflict with another, and that's the basis of the notion of agreed. Once we've got that reservation, and we'll get an ID for it, we can schedule a job against that reservation. And we can also do some important policy-based optimizations. We can clear unused reservations and preempt jobs that are in the way of a job with an active reservation. And the text on the bottom there in Courier shows how to do the reservation, in this case for a Z4 span 5, and then how to run a job against that reservation. Here it's an interactive job. Here's a graphic of this in action. We have the reservation scheduled at some point, and it will stop new SA jobs from being scheduled to its resources when it becomes active. Assuming we've got a corresponding ICE job is available before or soon after the reservation starts, we can ask the preemption service to preempt those jobs that are on that reserved resources. Those jobs that are preempted can either be discontinued or rescheduled into the future, as is the example in this case. The ICE job can now start and take the resources that were intended for it. The preemption does require cooperation from the SA jobs if it's to be efficient, and we'll cover that approach next. So now turning to the SA mode, which are useful for simulated acceleration regressions, and it uses a technique we're calling job chaining. While design teams always have their own way of working with emulation, our existing customers often use the following model for software-centric tests and simulation acceleration. First, there are many tests, perhaps coming in from several different software teams. We group those tests into sets, and each set is associated with a single team, though a team may have several sets. In our earlier product, we grouped all of the tests as a bundle and provided no visibility into the status of each test. This new version of Hero uses a different model where each test is fully visible in the queue and is a first-class job object. The design load time may be much longer than the test time runtime. So we essentially need to reuse the loaded design for subsequent tests to avoid this reload penalty. Now, tests don't always behave well, so we'll need some way of aborting the test. We use an expected duration to do that. And when the expected duration is greatly exceeded, we'll auto-kill that test and start the one behind it. Similarly, we might want to put an upper bound on a given test set so that each design team gets a fair slice of the emulator time. And then finally, we may cap the total time of that regression so that another one can get started. So here's how those multiple SA regressions might appear across 3 separate Z1 emulators. We can continue a regression, as in the case in the orange box for Reg 1. We can see that Reg 1 was started, ran for 4 hours, and then was essentially interrupted by Reg 4, and then which ran for 4 hours. And then we're able to reload the design and continue on with regression 1. And the other use case is perhaps so we have regression 3. Extra resources were available for that regression, and we're able to run it in 2 separate places concurrently. And Hero's execution model supports this, though your tests will need to be able to support the out-of-order nature that this would imply. Things don't always go as planned, and after all, we're reminded this is development. Jobs get stuck, test set overrun, regressions overrun. So we'd like to set a runtime limit on a single job, a group of jobs, and really an entire regression. And this ensures good throughput during the nighttime. So the primitives we have for this is auto kill on a test, say perhaps 2 minutes for a test that is expected to take 8 seconds. Then we're also going to have a max life on a tasker, and we're asking it not to accept any more tests after a certain period. And this is useful for limiting certain teams' simulation time to let others in. And this is the case of that 1 hour setting in the diagram for that blue subtasker on the right. We also allow preemption of the regression. Perhaps another more important regression is waiting. Perhaps it's got the later version of the netlist. And it also can be preempted should the session limit be reached. So with some primitives there, we should be able to implement a wide range of policies. And a reminder that because the tests are a first-class object, we also have the ability to run pre and post commands. Hero's built on Accelerator, a batch system that is unusual for providing easy-to-use color coding for jobs. We can leverage this for these test sets too. A green box represents a job that has a run and produced a legal exit code. A red box is a failed job, and we can click into that job to see why the exit code wasn't as expected. If we overrun our time limit, we may decide to dequeue jobs, and that's where the purple indicates. Our running test, and there should only really be one at any one time in a progression, is orange. The remaining tests are cyan, and those are queued. While this is a simple approach, it's proved its value over the years and enables many test sets and regression job status to be evaluated near instantly. A common use case is to run the same test job in successive regressions, perhaps as the design changes or conditions are slightly modified. We were asked if there was a way Hero could compare a job's status and perhaps a runtime from one regression to another. Now, Hero does have a built-in jobs database that tracks this data, but it's hard to tell one job instance from another. That's where we're actually trying to compare the multiple instances of really the same job. However, with a single hint, we're able to do that. Here we use the tool field to uniquely identify a certain test. Here it's called DDRsync. Now, many of you got your own jobs databases, and you can still use those. But for those who want something out of the box, that's a good way to get it. So summary and job chaining, it allows us to load the design once and then run many tests. We get full visibility and control those individual jobs so that they can be scheduled according to typical batch queue parameters like priority and fair share. Because the tests are first-class job objects within Hero, we can get excellent visibility into the regression progress and monitor multiple regressions concurrently. And we can make use of preemption without inducing a failure in the test job. Indeed, the regression can be resumed if necessary. This capability allows SA runs to work well with ICE and interactive jobs. So on to pipelining. Compiling a design may take several days. We'd like to be able to submit the test jobs in anticipation of the availability of that design. Concurrently, we'd like to continue to run jobs on the older design and cut over to the new one as soon as it becomes available. Hero can handle the distributed parallel jobs used in the flows like IXCOM and VXE, WXE in the Palladium flow. And the mechanism to handle the pipelining is to make the design loader or regression handler job dependent on successful completion of the compilation flow. And this is possible to do because, again, Hero is based on a regular batch system that supports job dependencies. So now we can keep the pipeline compilation and simulation acceleration runs. And this keeps the emulators busy and working on the most recent builds. In summary, Hero is a queuing solution that combines features of a regular batch system with those unique to the emulator queuing problem. It's an emulator agnostic and should work for all of the current emulators on the market, including prototyping systems like HATS. We've shown a few examples of how SA and ICE jobs and interactive jobs can be handled, and hopefully that has given you ideas on how to apply Hero to your own environment. It's a flexible system and can be tuned and extended to meet a variety of use case scenarios. If you think it's interesting to see how it can be applied to solve your own emulation problems, please contact us. Thank you for your attention.